Hi everyone, welcome to the video presentation for Lab 11 on Fluvial Geomorphology, which basically means how water shapes the land. Now, this lab we're talking about moving water, so a stream or a river, which moving water would pick up sediment and it may deposit sediment somewhere else. So this often happens as water moves downhill from high elevation to low elevation, depositing material, but this could also happen during a flood event such as a big rainstorm. So this has huge implications for structures or agriculture that's along the riverbank. And these processes are very dynamic. They change through the seasons, through different weather patterns, and also just over the years, the shape of streams and rivers would change. We're going to look at that in lab today. So there are different types of rivers. There's no one clear definition of a stream or a river. There are, however, different types, but they all follow the same laws of physics related to things like stream friction, water velocity. These can result in different flow rates for water, and this actually creates the typical curving shape that we see, especially on larger rivers, but even on the smallest of stream that may form in your backyard after a big rainstorm. We get these serpentine patterns. And over time, just due to the water velocity being greater on the outside curve of a stream versus the inside curve, this shape will change. There will be more erosion on the outside of the curve and more deposition on the inside. So to take a step back here, remember that that sediment is getting picked up just with moving water. Maybe if you were to dissolve salt or something in water and you stir up that water, more of those grains of salt or whatever, what have you, will get picked up in the water column. But if you were to let it sit for a few hours, say, most of that material would again settle to the bottom as the velocity of the water and that energy decreases. So this is the same sort of principle that governs how sediment is picked up by moving water. So we can have suspended particles, which are often very small. Even the very dynamic and active streams can even pick up larger pieces, small rocks, maybe even boulders, given a highly active, very turbulent stream. And these traditional fluvial geomorphology features that you need to remember are going to be point bars and cut banks. Basically, a point bar is the deposition that occurs on the inside curve of that serpentine shape of a stream. So on the inside curve, the water is going a little bit slower. So some of that suspended material or that picked up stuff gets deposited. It creates often really sandy bars, point bars on the inside curve. So this is opposed to the cut bank, which is basically the opposite. That water is going faster on the outside of the curve and erodes away the riverbank. So there's just greater friction between water and the riverbank itself. So it just eats away at the outside curve. Now, the Mississippi River is, it flows through a number of states, starts up in northern Wisconsin, Minnesota border, and it is a great example of how rivers can change over time, and it shows us some of these fluvial geomorphology features like the point bar and cut bank. So if you look at over time from 1976, this region in the lower Mississippi River in Arkansas, the Arkansas River actually flows into the Mississippi River. And if you look at it over time, there's changes to the river shape as well as the size, depth, and position of the point bars and cut banks. Now, there are also other features that you'll need to know, such as oxbow lakes, which occur when a meander, or basically just like a curve of the stream, gets so curvy. Think of a C turning into an O. So when that's what happens when a meander or a curve gets cut off from the main channel of a stream, which just leaves a crescent-shaped oxbow lake. So over time, this occurs usually very gradually. So the meander cutoff may build up slowly when things like wetlands or very shallow water. Over time, though, the oxbow lake can become completely separated from the main channel of the river. Now, how these dynamics occur are most simply related to stream size. And stream size can be defined by the depth of a stream and its wetted perimeter, which together create its area. The area of the water body that actually makes up the stream. So of course, streams vary greatly from just a ephemeral springtime stream that might run somewhere through the woods, or I'm sure you can think of examples in your own neighborhood, because these are very numerous. They're everywhere, and they may flow into larger and larger streams. So these small ones are called tributaries just because they tribute their water to a larger stream. And so stream size is really important for determining things like water velocity and just for how hydrologists define streams in general. So roughness also plays a factor, but we're just going to look at stream size, so the stream radius, wetted perimeter, and of course its area in the lab today. So you're going to do some simple calculations. The hydraulic radius is just the area over the wetted perimeter. So you have to do a little bit of math, just simple math in the lab for this week. But what this means for the dynamics of hydrology is that a larger hydraulic radius means more flow of volume. So this is like the best way to describe stream size. And stream velocity is related, but not exactly the same, because this is more so the speed of the water, which is, of course, due to the slope or the elevation change over distance. Of course, a steeper stream would have a much faster flowing water. So in mountainous regions, such as here in the Appalachian Mountains, the stream velocity is going to be highest when the elevation is the steepest, which is usually at the start of streams, at the very top of mountains, and gradually, as a stream works its way through the system, oftentimes the elevation becomes slower, but the hydraulic radius becomes larger as more and more tributaries feed into larger order streams. So this velocity, stream velocity, is related to erosion, of course, because with more movement of water, there's going to be more roughing up of particles, and there's going to be more suspended material as well. So together, stream velocity and hydraulic radius make up these sort of basic stream dynamics that form the basis of hydrology. Now, there are also drainage basins that that you need to understand here, where in Milwaukee, we actually have, we're pretty unique in that all of the water that may just naturally fall from rainfall in the Milwaukee River Basin, which um, is from Cudahy all the way up into Ozaukee County, and all these flow together to eventually make up the Milwaukee River, which then flows into the Lake Michigan. Now, this is unique because this water is flowing into Lake Michigan rather, opposed to most of Wisconsin, which flows westward into the Mississippi River, which is part of its own basin, which flows all the way down to the Gulf of Mexico. The Mississippi River basin is huge, and so all that water is going to work its way down to the Gulf of Mexico, versus where we live in Milwaukee, that river or that water is going to work its way out the St. Lawrence Seaway, eventually into the Atlantic Ocean on the East Coast. Of course, that may never happen or may take many years, but that's the direction of flow, which is dictated by these drainage basins, which hydrologists have defined for pretty much all places. Sometimes that changes, but generally this stays the same because these erosion patterns just reinforce these drainage basins to occur. Now, don't worry too much about the technical details of drainage basins. Just wanted to throw that out there. What you will need to know, however, for lab is the order of streams. This is referring to whether a stream would be a very small tributary, starting off like a very small stream, which would be a first order, and then first orders flow into second order streams, and then third order streams down the line. And this is a simple way to characterize the type of stream, other than just its hydraulic radius or stream velocity. We can also think of the order of streams, meaning whether this is just a small tributary, first order stream, or a third order plus, meaning it's fed by much smaller streams. So what this means, if you have a very significant rain event, you may have a few days of really heavy rain. There is going to be really high flow surges in these first order streams right away. But as that water works its way up the orders, this may take hours or days. Then there are going to be large flooding events because there's so much volume flowing very quickly into these high order streams. So the flooding is going to occur downstream in these high orders, but the high flow surges would occur in the lower order streams, but they drain very quickly. So that's how you can differentiate what this actually means on the ground, or rather in the water, what low order streams are versus high order streams are. So you're going to look at just a couple examples in the Milwaukee River Basin, actually along the Milwaukee River, and you have to characterize whether that's a low order, high order stream, and what sort of whether they would have more susceptible to flow surges or large flooding events. So this, fluvial geomorphology is really part of hydrology, which is its own standalone field. But we get exposed to this here because fluvial geomorphology is one of the major players in giving us the shape of land that we have today. We have these networks of streams that flow together. This is highly ordered once you start learning about how fluvial geomorphology occurs. And this, the classic example is the Colorado River over so much time forming the Grand Canyon. That's the classic example of fluvial geomorphology at work. But this occurs, in wherever you live. I guarantee there's some sort of stream that's shaping the land. Over time, things are going to be different. So that's why fluvial geomorphology is really important. Uh, you're going to be looking at just a few examples of locations where these are really evident, like on the in the Louisiana-Arkansas border, on the Mississippi River. And if you have any questions, of course, please reach out to me. Email or Teams is great. And good luck.